Hi everyone, in this video we're going to talk about section R.1, real numbers. This section is going to be an overview of some of the background material that we'll need later on in the course. So first I want to start by talking about classifying different numbers into sets. Okay? This is often done in mathematics. It's often helpful to classify what numbers we deal with and what kind of groups they're in. So what do I mean by that? Well, we can classify numbers into groups, and so a certain group that is often popular is called the natural numbers. Okay? The natural numbers are the group, or we'll call them set here, and set is something very important, but we're going to sort of skip over that. But you have the basic idea of what it means. It's the group of numbers 1, 2, 3, 4, and then it just keeps on going as long as it can to infinity. Okay, so the numbers that start with 1 and go up to infinity, counting by 1, are the natural numbers. The whole numbers are almost the same as the natural numbers, except they include 0. Okay, so everything that's positive, all integers that are positive, an integer means it's a whole number. These are sort of technical terms, but we use them in non-technical ways, so it can get confusing. Okay, integers greater than or equal to 0 are whole numbers. Okay, then that gets us to sort of a larger group, which I just talked about, the integers. Integers is any number without a decimal. Okay. So nothing after it, just the whole number. But they can be negative. They can go all the way from negative infinity all the way to infinity. Okay, so those are the integers. And then we get to some more, maybe a little complicated numbers, the rational numbers. A rational number is any number that can be expressed as the quotient of two integers. And so you want to remember that the quotient, when I say quotient, I mean division. Okay, so two numbers divided by each other is a rational number. So for instance, 4/9 is a rational number. I have integer on top, integer on the bottom, and I'm dividing them. So that's a rational number. Rational numbers can also be decimals. Okay, as long as their decimals terminate or follow a pattern. So what do I mean by that? If we take 1/4, okay, 1 divided by 4 is 0.25 as a decimal, and there's nothing after the 5, so it terminates or it ends there. And then 1/3, 1 divided by 3, is 0.3333, and the 3's keep on repeating, but that's a pattern there is a pattern there that every number is 3, okay, or every decimal place is 3. The decimals keep on going forever, but they are 3. So that's what I mean by a rational number. Now we'll get to maybe an even more weird set, okay, of numbers. It's the irrational numbers or irrational numbers. Irrational numbers are like rational numbers, okay, very similar, but their decimals do not end, okay, so they have to keep on going, they don't terminate, and there is no apparent pattern. They don't repeat themselves. So the most popular irrational number is pi. Okay, pi in its decimal representation is 3.141592, and then it keeps going, but there's no pattern. It's not like 141592 repeats itself a bunch of times. The numbers keep on going, and there's no apparent pattern on how they go. Okay? So that's what I mean by irrational numbers. Now, why am I talking about all these sets? We're getting to the most important one that we'll use most often. Those are called the real numbers. Okay? The real numbers. It doesn't mean that these are real and then there's another set of numbers that are like fake. That's not what I mean by real. Okay? The real numbers are the union of the irrational and rational numbers. So really that means it has decimals. They can repeat, they may not repeat, it doesn't matter, they're part of the real numbers. And so here's a nice visualization to help us think about rational and irrational, the real numbers and what they encompass. So all of that stuff that I had on the first slide is over on the right side of the picture, okay, where the natural numbers are smaller, are contained by the whole numbers, which are contained by the integers, which are contained by the rational numbers. And then on the other side, ones that are completely different than the rational numbers are the irrational numbers. And when you put them all together, they make the real numbers. Okay? So a union means I take whatever is in either group. Okay? So the real numbers. Great. So where do we actually get to do like some problems or something? Here. Here's where we start to actually do some stuff. When evaluating expressions that have real numbers in them, there are certain mathematical laws that govern how you have to work with them. You've been learning these mathematical laws ever since you took a math course, ever since kindergarten or maybe even before. Of course, they don't present them to you like complex mathematical thoughts, okay, because you're too young to sort of understand them, but they're there in the background, okay? And so when we evaluate expressions like this, 8 plus 2 times 3, it's important to remember your order of operations, okay? And so people think of it in a number of different ways. I think the way that I learned it, is PEMDAS, okay, parentheses, exponents, multiplication, division, addition, subtraction. There are other sort of phonic things that you can remember, okay, but hopefully this is not a challenge for you. So how would we evaluate 8 plus 2 times 3? Well, the first thing that you have to do is look for parentheses. No. Exponents? No. Multiplication? Yes. So you multiply 2 and 3 first, and that gets you to the expression 8 plus 6, and then you add 8 and 6 together to get 14. Okay, great. If that was the whole class, I bet we'd all be happy and go home with A's. Unfortunately, that's not. We can dig deeper and examine the mathematical properties and rules that govern working with real numbers. Okay, and so these are the rules in a bit more technical definition than you've probably seen before. So, properties of real numbers. These are some of them, but not nearly all of them. Okay, so when you work with real numbers, which is what you've been working with your entire life, okay, when two numbers equal themselves, okay, 8 is equal to 8, then you can sort of flip it around and say 8 is equal to 8. If you imagine they're like objects and you do flip them. They look the same because they are the same. That's a reflexive property. The symmetric property means that if A is equal to B, then B is equal to A. Okay? If A is 8 and B is 8, then they're both equal to each other, and I can flip that around on either side of the equal sign. The transitive property says that A is equal to B and B is equal to C, then A is equal to C. Okay? So these are things that we all know. Okay? But probably you haven't thought of them as the transitive property. Right? And then the last is the principle of substitution. For this first part, if A is equal to B, then we can substitute B in that has any expression containing A. Because they're equal, nothing's going to change when we do that. All right, so that's some of them. Here's some more. Okay, A plus B is equal to B plus A. Okay, 2 plus 3 is equal to 3 plus 2. That's a commutative property. Okay, and 2 times 3 is equal to 3 times 2. Okay, so those work in that way. And you may think, well, yes, they always work that way, but there are other things, maybe numbers that aren't real. There are other types of numbers that don't fit into the real numbers. Okay, and they may not have these properties. It's something really weird to think about, but it's true, and so that's why we're talking about them. Those are commutative, and then there are also associative properties, okay? And you can look at them and take a few seconds to try to think about what these are saying. But the ones that I want to focus on, and the ones that we're going to do most with in this section, are the distributive properties, okay? And so this is the distributive rule that hopefully you encountered before, okay? If I have a number a, and I multiply a by b plus c in parentheses, okay, then that a, the multiplication, goes to both the first thing inside the parentheses and the second, okay? And furthermore, if there were more things, plus d plus e plus f, so on and so forth, in the parentheses, a would go to each of them, okay? So that's one distributive property. The same thing said in a different way. If I have the parentheses first and then multiplication, it works the same way, okay? So the c is on the right, but it still distributes to everything inside the parentheses. So let's go with that and do some examples, okay, of both distributing in and distributing out, okay? So hopefully you've had some experience with all three of these types of examples before, but I'm going to work through them fairly quickly, okay? And then, after this slide, you're going to have a chance to work on your own, okay? So we'll start with number 1 over here, okay? 2 times x plus 3. By the distributive law, that 2 is going to go to both the x and the 3. So in simplifying this expression, I get 2x, maybe I shouldn't skip a sec, 2 times x plus 2 times 3. Okay, great. 2 times a symbol is just that written that way. I can take away the dot because that's understood to be multiplication. Okay, and 2 times 3 is equal to 6. And so the answer is 2x plus 6. I've simplified that expression. Okay, now what if I want to work backward, okay, and simplify this expression by taking out the x, okay? You might say this expression is already simplified. I may say I want you anyway to take the x out, or work the distributive rule backwards, okay? I notice that there's an x common to both the 3 and the 5, so I can, many people will say, pull it out in front. X times 3 plus 5. 3 plus 5 is 8. And so I get 8x. Okay, so you might have said, well, yeah, you just add 3x and 5x together to get 8x. That's great. That's a shortcut. This is sort of the long way around to do it. Okay? But anyway, we've simplified the expression, 8x. Now, to the last one. Okay, to the last one, we're going to use the distributive rule multiple times, okay? And many of you will know this, x plus 2 times x plus 3, the method to solve it, you might call it FOIL. First, outer, inner, and last, okay? That's just a special distributive rule instance that's used a lot, okay? So, to simplify this, I'm going to distribute the x to both the first and the third place. Okay, first and second inside this term. Okay, and so I get x times x plus x times 3. Okay, so I distribute that the first part of the first parenthesis expression, okay, to both, and then I do the same thing with the 2, okay, plus x times 2 plus 6. or 2 times 3, okay? I'm going to say we can do 2 times 3. And so we get x squared plus 3x plus 2x plus 6, okay? And then I can combine 3x and 2x to be 5x, okay? X squared plus 5x plus 6. So that is using the distributive rule to simplify expressions. All right, so in the next slide here, you're going to do what's called a your turn. Okay, this is the first one that you've seen, but they will be around a lot. Okay, in these your turns, I want you to work out each problem. Okay, you'll see that they're very similar to what the examples that I just did in the previous slide. I want you to work them out, and there will be a space online to turn them in. Okay, so there's going to be a drop box in D2L where you can turn in your assignment. So I want you to write out your work, scan them, and turn them in. Okay, your turns are part of your homework assignment credit. Okay, so they'll be these are for completion only. It doesn't need to be correct. Okay, I just want to see you try to work them. Okay, but you need to do them and turn them in on D2L. Okay, or else your homework score will suffer. All right, so I don't mean to end that way on a like bad note. Okay, not a bad note. Just please do them. All right, I'll see you next time.